while I'm at it, I'm also going to do problem number 59 today. So let's say that we have these tiny blobs. Let's say that they're spherically shaped, because it seems to be assuming that. Converting these to centimeters, it makes things far easier. This is actually quite the easy problem if you can see past the conceptual bits. So, without further ado, let's start on the first problem. Excuse me while I get a calculator. Pause. We obtained that the masses of the water droplets are roughly 4.18 nanograms. Now let's convert these back to kilograms and meters, as we are only using these for the sake of convenience and density calculations. So we have this. And we know what gravitational acceleration is. We'll say down is positive for convenience. Or actually, no, we'll say up is positive, since this force is going up. Now, what we do is, we note that F equals ma, and we then write the forces that need to be balanced out. Okay. Now note this thing which kind of got stuck in the free body diagram at the start of the problem. With this said, let us now compute the values for the next few. We're keeping this dimensionless for the sake of simplicity. We'll just completely ignore the second term. As we can already tell from the first term, that the second term is going to be negligible at this scale. Solve for V. Second one. Well, this one is a bit more interesting. If we were to just divide this by this and get velocity, this over here wouldn't be a negligible factor anymore. So now what do we do? Oh, right. Actually, even with the new values, neither is a negligible factor anyway. So instead we do this. Watch carefully. A here is 8.7. Notice how we can do this. Obviously, the velocity can't be negative, so we'll rule that out right away. Now, for the final one. The velocity is bigger than 1, following the trend from the earlier ones, so we'll ignore the earlier term. And voila. Let's pause. This one was supposed to be 0.0132, but all calculations up to that point are correct. As you can see, our answers match. And that's it. Today we are doing problem number 51. To understand how this problem works, it is essential to know how a spring scale works. First of all, note that if you have two forces of equal magnitude on each end of an object that will not stretch, the tension of that object is equal to one of those forces, not the two summed up, one of them. Let us suppose that Pat here pulls with a force of X newtons on the entire system. Let's say that let's say that of these X newtons, X over 2 are transited through the spring, which exert at the bottom, which exerts a normal force upward, and X over 2 at the top have another normal force exerted on them. The reason for this is that it is assumed that the spring is not accelerating downwards or having unequal tension throughout itself, so it cannot be exerting different normal forces. In this case, both of the normal forces and both of the forces would have to be pretty obviously X over 2. With that said, the tension of the spring is X over 2. So Pat is pretty obviously exerting 500 newtons. Now let's draw some free body diagrams. Does he exert normal force? Yeah, I think he does. Otherwise, the chair would just accelerate into him. Or no, there's no need for him to exert normal force. Anyway, so now we have this. And now we have this. And that will do for free body diagrams. And it's because I can't draw. With that said, let us now define let's say MC is the chair's mass, MP is the person's mass, and M is the sum of them. There, that allows us to conveniently define this. So, we define, also let's draw some free body diagrams for the sake of rigor, or I mean some coordinate systems. Let's see, where was I? Oh, just a bit of context. Next, M multiplied by G is equal to 480 newtons. As it is equal to 160 newtons, the chair's mass, plus Pat's mass, which is 320 newtons. So we can say M is equal to about 49 kilograms. So we can state that and with a few calculations, we reach our answer for part B. Here, the textbook does something that I think is really stupid, but I don't feel like arguing with it right now because it's 10:15 at night. Right? It says that the only force that Pat exerts on the chair is the 250 Newton force the spring scale is exerting, in spite of the fact that he is exerting 500 newtons on the entire system. But anyway, or I should say on the chair system. So, we define a special acceleration, A pat, so we get A pat is roughly 5.004 meters per second squared. Is that the case? No, it's 5.104. Ignore that. Now, we get that the chair's mass multiplied by gravity is 160 newtons. This was given at the outset. So the chair's mass is roughly 16.3 kilograms. We should state this rigorously at the start of the problem because, well, it's obvious. as I was saying. So we now state that the force, because F equals ma, we now state that the force exerted on the thing is equal to the acceleration Pat is causing, multiplied by the mass of the chair, which is equal to about 83.3 newtons. By the way, there's a much simpler way to explain the thingy with the spring. If we assume the spring scale is measuring the tension in the spring, then we assume the tension in the spring has to be constant, assuming a constant force. And in that case, since it isn't anchored to an immovable object, and having a constant force on one end, which would cause tension, the only way for it to have constant tension is to have equal forces on both ends, which would imply that these two forces, we'll call them F1 and F2, sum up to X, and that F1 equals F2, which would imply that each of the forces is equal to X over 2, which would imply that whatever force Pat would have had to exert on the end of the rope in order to exert some amount of tension in the spring, and therefore read a certain reading on the spring scale, is twice that amount. And, okay, that's it. That's the formal solution.